Okay, so let's let's start. Okay, so welcome everybody, and it's a pleasure to introduce the speaker today. It's Jordanin, that comes from ESADE, that is a university in Barcelona. You have it here, Ramon Llull. Okay, so it is named after a Mallorquin person. And before, I mean, Jordi did the PhD in an institute of the SIC, the one of artificial intelligence. You have here all the story. Okay. So because I have to do the presentation, that's good. Okay. Did a postdoc at CNRS. It's very easy because now I can follow the thing. Stay at the UPC. BSc also, so the BSC, the Barcelona Supercomputing Center. And after that, he was working in BBA Data Analytics for a while. That is when we started to collaborate. He was the boss of Pablo Fleorkin. Maybe some of you remember remember him. He was one of the PhD students here at IFISC. And after that, he went to ESADE, and we will nest back to CSIC, unless you decide that it's a crazy thing, I don't want to go back. And he will incorporate to the Artificial Intelligence Institute in Barcelona, okay? So, well, that's a little the story that you have in the slide. And, well, it's a pleasure to have you here. The floor is yours. Okay. Just switch on the micro.
Can you hear me?
Check that the microphone.
Sí, yo en verdad. Tobias, can you hear me?
Yes.
Thank you so much. Okay, so thank you so much, Jose, for the introduction. I wasn't the boss of Pablo. I was the supervisor. Boss a little bit. I don't want to be bossy. So my talk today is about a research line that I have been working for a while, around 5 years, more or less. We started to work in that topic for an industrial need, and it was the main topic of one of my former PhD students. And you will see that all of the examples, or most of the examples, came from the need of a bank. So don't feel bad if everything looks, so all my examples are related with the banking industry, because it's an industry that is highly regulated, and this means that there are a lot of constraints about what you can do or not with an AI system. And so it's a good example, it's a good type of companies where you need to be very conscious about what you are doing with your data and with your predictions. Vale? Yeah, that's basically the real need for all the research. This is the outline for today. I decided to add like an unrelated complex network topics because maybe you didn't really aware about the problems that we have in Barcelona or in the peninsula in general with the electricity last Monday. Maybe yes or no. But since I'm advising a PhD in complex network, so I will explain more or less what he's doing because it's related with electricity supply. I promise it's just a minute, 3 slides, just if you're interested. So basically, the thesis started by this problem, or this question is like our president decided to establish a special regulation for the gas price in Spain. And it was called the Excepción Ibérica. I don't know, are you aware about that? So we pay a different price than other countries about the gas, just because there is a policy that regulates a little bit the price. And then on that period, because Bernat started the PhD in September 2022, one of the researchers at the study that is more about economics published these papers explaining that thanks to the policy, the Spainers are going to pay less. And then we start thinking, we are paying less because of the regulation, we are paying less because of the network topology, we are paying less because, no? So we couldn't see any clear causal relation between this difference between the real price and the expected price before this excepción ibérica, ¿vale? So basically we start playing a little bit with the data, and then we came up with some solutions to evaluate if one dynamics that you observe in a network is because of the network or because of the dynamics itself, and the metadata and the regulation, the external regulation that someone puts on top of the network. No? So we published a couple of papers. This is one example. It's not an exponential graph model. I know that maybe in physics it's more common. This is more about rewiring because we are a computer scientist. But if you're interested in some kind of statistical tools to evaluate how important the network, the topology is regarding a dynamic, you can play with this GitHub and get these plots. ¿Vale? And apart from that, last year, Bernard went to Harvard, and then we start collecting data because collecting data in the electricity network in Europe is a mess. It's almost impossible. It's everything quite secret. But in US, they are a little bit more open. It's horrible because it's mainly ruled by private companies, and you need to contact and do web scraping to many different providers of electricity providers. But at the end, after 6 months, we were able to get all the network information from the US Northeast area. We are going to publish and release the dataset in summer. So if you're interested in analyzing something, I don't know, do a percolation test in this network, just contact us because we are going to publish the data in a few weeks. Vale, so this is just outside the topic, just for the importance of the electricity shortcut on Monday. And so let's start with the main topic of today, that is about how you can create a copy or how you call it, a twin, or call it as you like, a surrogate model from an already trained machine learning model. ¿Vale? And this is important because a few years ago, the European Union created like a group of experts just trying to guess which are the properties that an AI system should provide to users and the society. And then after some years and a lot of money, they wrote this sentence saying that an AI system that is not the same than a machine learning model, we will see some difference later on, should be designed and operated in a way that is safe, fair, transparent, and accountable, ensuring that the decisions and behaviors are trustworthy for users and society. I don't know you, but I have no idea what does it mean. But I mean, it's super open. But they create like some kind of pillars, some kind of properties, where they say, okay, if you want to have a trustworthy AI system, you need to ensure these 7 properties. And all of them are interconnected. ¿Vale? I will not go through all of them because it's just 1 hour. This will only take me 1 hour. So I will just give you like some points that are important to understand why in a bank there was a need to pay for an industrial PhD doing this research. No? These different pillars basically at the end results in that we need to keep the privacy of users. So we cannot, any AI system cannot release private information or sensitive information from someone. ¿Vale? AI system should be transparent in the sense that we need to provide, or the company should provide an explanation about what the machine learning system is doing. Should be fair. I cannot make a different treatment to Jose because he's a male or you that you are a woman. That's not possible. This is unfair. We need to guarantee that AI systems are not being unfair with some collectives. Accountability. If something is going bad or wrong, then we need a system to make someone accountable and responsible for the problem. We cannot say that, oh, something like like on Monday, no? We stop distributing electricity for any reason, and no one, and the system say, oh, I will just stop something, and there is no responsible for that. And then should be sustainable. And this is quite important. So I don't know if you are aware about which is the cost of training ChatGPT. Any idea? How many millions OpenAI invest to train ChatGPT? Just in the electricity consumption. Any number? Little bit less, but yes, around that value. 20 million only the electricity bill for training the model. So it means like starting for a huge matrix with numbers at random and train these values to get something that can be used for doing a large language model. And this means, no, the whole training, no, the last training, and this is quite important, the last training. So training the actual GPT-4 cost around 8.5 million euros in electricity, not the previous ones. So all the times that you train a model and you fail, this is just coste hundido, as we call in economy. ¿Vale? So can you imagine the total cost and that's another important data. Do you know which is the price of ChatGPT that OpenAI is paying every time that you use it and then the prompt told to you, oh, very nice question, thanks a lot. Just for this word, do you know which is the price that OpenAI is paying in the electricity cost for outputting these nice words that are synthetic sugar that's being nice with you when you are using the tool? How many millions they are paying just for repeating the...
That's not training, that should be cheap.
Token generation that costs some money every token.
Compared to training, that should be...
No, but you have million users. And a lot of teenagers are asking silly things. ChatGPT, well, again, several millions of euros per year. Just saying thanks to the users. And do you know which is the difference in electricity if you use Google Translator or ChatGPT to translate a text from Spanish to English? How many times you multiply the electricity cost of using ChatGPT instead of Google Translator? But it's a special AI system that is designed to translation. How many times do you think that you multiply the cost? 15 times. So every time that you decided, instead to go translate.google.s and translate a text using this tool, and then you say it's more comfortable to just copy and paste your prompt and ask ChatGPT, please translate this text, you are using 50 times more energy than the previous option. So sustainability.
But that's just for the use, not for the...
No, inference. I'm just talking about inference. Only inference. So inference means you have your GPU, you have your matrix stored in your GPU, and then you put a list of tokens, and then you propagate the electricity to compute the multiplication and get the output. Nothing else. I'm not talking about training, no? I'm not creating batches, just inference. DeepSeek, well, I don't know if you read any of you read the DeepSeek paper? No, well, I did it and it was impossible to understand what they are doing. It's impossible. I mean, it's designed to hide what they did. Why? Because many experts are saying that they basically break the rules and regulations of OpenAI. They use like GPT-4 or OpenAI or other APIs to create something that is called knowledge distillation and then being able to compress the model. But since this is not proof yet, no. But in principle, in performance, it's exactly the same, quite similar. I mean, but again, the benchmarks are still pretty new, so they compare sometimes peras y manzanas. But in principle, the performance is quite similar and they use much less energy. In fact, you can download the model in your own laptop and use it without having a GPU if you want. But assume that you are sending your data to China. That's the price, ¿vale? Well, this is just a side note, but having this idea in mind, no? That training is expensive, ¿vale? Okay, so now let's go and try to understand what is the idea of want to reuse a model, what we call practical constraints or deployment constraints, or any constraint that is basically external to the AI system that is imposed and we need to adapt it, ¿vale? I don't know you, but this is what I've been doing for 25 years, more or less, because I've been working in AI for a while. So in general, both in academia and industry, I follow the same process, no? Jose, you are also quite expert on that. So I gather some data, then I start crunching my data during a while, no? And then when this is done and I try 100 different options, even if I feel lazy and it's Friday afternoon, I create a grid search and then I send this huge computation to the server and I go to my weekend and then I come back on Monday and I just check which is the output of which combination of hyperparameters perform the best, and I select this as my best model, and I'm super proud of me because I found a very nice machine learning model. No? See? Are you following the same policy? See? No. Come on. So, and then when this is done, I train my model with the hyperparameters, and then I move it to the inference, and then is when I am starting using it in production. What happened of that? That this is super costly. I've been trying 200 different models without thinking, just because I'm lazy. And this is just for creating the model. It doesn't mean that we deploy them and then we start using it in real life. Imagine that you are a company and then you are starting using this we call in production, but in real life. And we are not taking into account any possible change in the environment. So, and this is another question for you. What do you think that on average is the lifespan of a machine learning in a company in production? So for example, when I work at BBA, I stay 1 year with Pablo, creating a model that wants to evaluate the real expenses of our customers. Because when you go to a branch and then you can prove your income pretty easy with the rent, but you need to know which is the amount of money you have available. So the cashier in front of you asks, which are your expenses every month? You say, nothing. Because you want to maximize the probabilities of getting the loan, but this is false. So we spent 1 year with Pablo just doing some profiling and trying to guess which is the reality of the customers. ¿Vale? How many months do you think that our model, or one model created like this, is working correctly in the real life? .6 months on average. So it means like every 6 months, we need to change this model and retrain it or create another one because the performance is suffering from a degradation because the world, the environment, the customers, everything is changing. But not only that, it may happen that appears a regulation and say, you cannot continue doing this. Typical example, inference, because I think that you like it. Imagine that you are deploying a credit card fraud algorithm, ¿vale? And you want to use it. So it means like every time that you tap your credit card in a shop, there is an algorithm that decided if this transaction is genuine or fraudulent. But you don't want to wait. No? This verification should be executed in less than 1 second. So imagine that there is a regulation saying, no, now it's half a second. You cannot stay 1 second for the inference process. You need to change completely your model. And this is not because of model degradation. It's not because of the data. It's not because of the data drift. Nothing. It's just a change that is imposed externally to the model. No? So at the end, you work hard, and your work is only useful for weeks or few months. So you need to reuse it and change it a lot. Well, this is called, we call it this environmental adaptation. It means like, I will just give you the notation, it's super easy. So this is the model that you deploy, and then you need to change it. So there is a task in a domain. A domain could be, make it super easy, some attributes, socio-demographical attributes with some values, no? The age, the gender, the income, whatever, ¿vale? And then you have your training data, you have your output, and then this hypothesis here is the family of models that you would like to use. For example, a logistic regression. I will use, I'm assuming that every of you is familiar with a logistic regression model. So I can use it as an example. And are you familiar with a decision tree? So can I use it as a matter of, so just to avoid to use like neural networks or more complex stuff, ¿vale? So, what this notation is telling you is that you would like to solve a task, predict a classification with some data, you have a training data, you have some samples that you already know the output, and this is the type of models that you can create. For example, all the possible values for the weights of a logistic regression or the possible splits in a decision tree. ¿Vale? Is that clear? And you need to create this model on a set of constraints that you define at the beginning. For example, the inference time should be at most 1 second. Is that clear? Then what happened? Everything is the same, but you want to change the constraints. There is something, for example, now, what's the name of the IT lady? Antonia. Antonia decided that it's time to update your Python distribution, and then you cannot use TensorFlow 1.2 anymore, and now you are using 1.5, and then everything works different. See? But is that clear, the scenario? And this is different of domain adaptation. That is basically, we change the data. This is super common. Imagine that you would like to move a model from Spain to France. There are some variables that more or less can change, like the average salary. Or transfer learning, because we change the task. This is super common either. So you train a model to recognize images, and then you specialize it to recognize dogs for any reason. ¿Vale? And also, this idea of environmental adaptation is a little bit more general than knowledge distillation. I will not enter in Hinton's research, because I know that maybe you are sensible with that, but well, this type of things is more a framework than knowledge distillation, because knowledge distillation uses what is called soft labels. Do you know the difference between soft and hard labels? So hard labels is, imagine that you are using a logistic. Hard labels is the final output after the threshold, so 0 or 1, and the soft labels is the probabilities associated to every label. ¿Vale? So for 0, I'm 1 or 0.35% sure that this is a 0, and for 1, I'm 0.65. ¿Vale? See? Yeah, so knowledge distillation assumes that you're using soft labels, and we are going to use the hard targets. ¿Vale? See? Okay. So let's try to give you an example of all these three settings. No? So here, this is like the all possible values for your betas in your logistic regression. This is your task. This is a level curve, assuming that you know that the beta is in the center. No? So if this is your task, this is your possible values for your betas. This is the best model that you can do. No? So in this case, this is transfer learning, because you are moving from one task to another. So you are just moving from here to here. Easy. This is what Hinton is doing. ¿Vale? So this is the task, this is the possible betas, and then you say, mira, my friend, you cannot use more than 5 dimensions. So even you have 20 possible values for your betas, 15 of them should be 0. So you are adding a constraint about all the possible values of your betas. So this is the possible values in that case. So that's the optimal value. But now imagine that you cannot use a logistic regression anymore, and then you need to use another family of models. What happened? that you go out of the feasibility set that is here. So there is no way that you find this point because this point is not part of the possible betas that you can use in logistic regression. You need to completely change your model. You need to move from a logistic regression to a decision tree. Is that clear? Vale. So let's see how we can do it. So how we can achieve this differential replication through copy. Vale? So we have a hard classifier. We will call it original. So this is our original model that we have been trained, and we want to update it. And this is quite important. We will not allow ourselves to query or to ask to the original training data. How many of you cannot submit the review of a paper because the training data was lost? In my case, a couple of times. But assuming that a company is going to keep track of all the training data, of all the models the company has deployed through all the story, this is impossible. So we are going to assume that for any reason, the training data set is lost. Is that clear, this limitation? So we don't have access to the model. We only have the hard outputs, and we don't have access to the training data. And now our task is take a model and mimic its decision boundary with a different model. Is that clear? Vale. Sí. So the goal is to obtain a new classifier, a copy classifier, with some parameters that we can fit that mimics or replicates exactly the same as before. Vale? To achieve this, we need to compute a discrepancy. We need a way to evaluate how different my new model is from my previous one. Well, this is like the empirical risk minimization framework. It's like the basic framework in machine learning. Even it looks super difficult, it isn't. So these are the hyperparameters of your model. This is just a capacity. It's just a measure too, because you would like to, in machine learning, you would like to create the simplest possible model. Vale? It's just saying that from the data and the possible model that can solve your task, select the easiest one, because this is the Occam's razor. The simpler, the better. Vale? And then we are going to assume that we want to impose this discrepancy. And this discrepancy basically is saying, compare the output of my copy with the parameters and the output of the original classifier, and then compare it, this is just a norm, and compare it with a model that ideally can replicate exactly the same behavior that we observe in our original. So that here basically means like, hey, let's not put this constraint that we want a simple model. We are going to create a model that can memorize everything. This is just for theory only, eh? See? So we want to minimize, so we want to find these hyperparameters of the simple model that are just guided by this constraint here. Is the problem understandable, more or less? Vale. Well, one option is we need to compute this thing, vale? If we can compute this thing, we are dead because we cannot compute our discrepancy. Vale. Well, the solution, so equation one, vale, is basically what I said, no? Producing the simplest model while minimizing the empirical risk. And there are two options. The option number one is the solution of the unconstrained model that we know that we can make it because we can create theoretically, we can create a model big enough to memorize everything. This is what deep learning does, basically. If in the possibility of our allowed models is the solution of the unconstrained problem, it means like we can memorize everything, so the error is 0, so problem solved. Not difficult at all, vale? And why this is possible and this is important is because we are working with the hard probability. So imagine that you have 1 million samples, you have a combination of millions a million 0 or 1, because if imagine, let's assume a very simple and straightforward classification, you can find a model that in principle can memorize exactly your output. Job done. You are able to copy a model with a different one that exactly replicates the thing. And that this is just because the problem is always separable. What's the problem? That in general, for solving or for going to that solution, we need to create an infinite synthetic data set. So it means like, no, you can generate new samples, you use the original as an oracle, and then you generate an infinite number of samples, then you label this infinite number of samples, and then you create a super powerful machine learning model that is able to predict with no error this infinite number of labels. So this is impossible, ¿vale? So we need to work on other options, ¿vale? But it's clear how it works. Any questions? You can interrupt me whenever you like. Is that clear about the framework? No question? Vale. So at the beginning, we say, okay, let's go for the simplest thing we can do. Let's assume that infinite is not infinite. Infinite is a very large number. And then let's go and see if we can generate a large number of samples and then try to solve the problem in a different way. So, and this is just an example. So we imagine that you create this is the make moons in scikit-learn, you create these two labels, then you train a neural network, then from the neural network you obtain the decision boundary, and now it's time to copy it with a decision tree. What this single pass copying is assuming that A, infinite is not infinite, infinite is a large sampling data. I know because of the dimensionality, the sample of the sphere, I'm not a physicist, I'm a computer scientist, so I'm not worried about that thing, but yes, sampling is a problem, ¿vale? A sampler, create an appropriate sampler is a problem, ¿vale? But no, imagine that you have this thing, and then you generate a large number of synthetic samples at random, ¿vale? And then use the original model to label them, and then you use this labeled synthetic data to generate your decision tree, and magically at the end you have a new model that the decision boundary looks like the original one. Here you are using a nonlinear thing, and here you are using a decision tree that is kind of linear. ¿Vale? See? So what we did is basically this idea of differential replication. You have a problem, you cannot access to the original data, you don't want to access to the internal of the model, and then you only use a synthetic data set, the hard outputs of the original model, and then you retrain and you create a model that preserves the decision boundary. This is something that you want, and the architecture is completely different. See? Is it clear? So in principle, this is not interpretable, and this is interpretable because you can plot or create like a set of rules to interpret why one point is pink or red. ¿Vale? Again, this is quite costly. It works, but it's quite costly, and we need to make it a little bit less costly. So we start working a little bit more, and 2 years ago, we published in this Journal of Machine Learning Research an alternative to the single pass copy. And here the main, I will not go to the internal details, but the idea here is we can generate an infinite number of samples, but we can do it little by little. So we can generate 100 samples, label them, do something with them, and then we generate another 100 samples, label them, do something with them, and then we can generate another 100 samples, label them. And if you repeat this process an infinite number of times, what you're going to get? An infinite sample. See? Vale, this is the idea of the sequential copy. And here the idea is, is repeat exactly the same, but doing this one pass, so the previous step, little by little. You start at random, you generate a model, and then you train it with 100 samples, and then you generate another 100 samples, and then you train it again, and train it again, and train it again. This may look a little bit tricky, but for a computer science, from a computer science point of view, has an advantage that you don't need to store in your hard disk an infinite number of samples. The only thing that you need is to have the capacity to store your weighting, the model in your computer, and then you are training little by little. You are paying time, so you are paying more computational time to save space, ¿vale? But also, it gives you a little bit of opportunity, so it allows you to play a little bit the way you are training and generating your samples. And this is what I'm going to see in the experiments, ¿vale? So the framework is clear, and so I will just show you some experiments to prove that this works, and then some application in the banking industry, ¿vale? So let's use a very simple example. This is the spirals, again, scikit-learn data distribution, and then the task is basically recognize if it's a spiral like this, and this is, I don't know what this color is, red and green, no idea, ¿vale? And now, this is the original data, label them, we train in that case a Gaussian support vector machine, and the task is, I would like to replicate the same behavior, but without accessing to the internals of the model or accessing to the training data. And here, basically, you can observe different things. These dotted gray lines here is the single pass option. So generate a limited number of samples and train your model and observe the accuracy, which is basically how many samples are you able to correctly label, to correctly classify. And then with 100, 200, 300, 400, 500, 700, blah, 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 until 1,700 samples. No? As you might imagine, the larger the synthetic data, the better the model. Pretty easy, no? Pretty straightforward. And this is a value about the accuracy in the following setting. It's the sequential approach, but what we are doing here is we start with a random neural network, and then we fit the 100 samples, and then we train it with a batch, and then we discard these samples, we generate another 100 samples, we train again as it was another batch, and we repeat this process, in that case, 31 times. And of course, the more samples that you are providing to the model, you are getting a better and a better performance. But you are never reaching the same performance that what you observe with the single pass. My question is why? Any idea? No, because at the end, here you get 100% with 1,700 samples, and here 100 by 100, we are reaching twice number of samples. So this model has been accessed to the sample 2 times more samples than this one. So this model here. Why do you think you are not getting the same amount of performance, even you are providing 2 times more data? No. It has this issue has a name in machine learning. A very nice name, and you know that machine learning experts decided to change the name for everything and put very fancy and marketing names. No idea? Well, this is called catastrophic forgetting. What it means, like your neural network is when you fit with the stochastic gradient descent and you update the weights, what you are doing is learning the new samples but forgetting the previous ones. And then this is the reason why you never reach like the same performance, ¿vale? And this is a problem. See? And this red line here is the sequential, and we are doing a little bit of it's a trick. So we are not dropping the previous sample. So here you have 100, 200, 300, 400, 500, see? And at the end here, you are getting in your data in your data set a larger amount of samples. So you are training your model following this one single pass approach several times. So we are basically cheating. See? Is that clear that we are cheating in the red line? Vale. But this gave us an intuition of saying, hey, my friend, with 100 samples, if we start from a good point, we can get like a quite nice accuracy. With 100 samples, the accuracy was 0.55. So, and this is just the initialization, ¿vale? So, can we fight again the catastrophic forgetting? And well, the answer is yes. And basically, how we did it is we just define a norm, a very simple norm, the simplest norm that you can define, and this is the uncertainty. This is basically measuring in which sample your copy, your new model that you can access to the soft targets, because it's you who is designing the copy model, and this is just the hard label compared with the soft label that you have the copy. So this value, it may happen two things. If your copy is wrong, you will get a large value because you are outputting a 1 or a 0, so you should get the other one. But even if you are correct, so your output is correct, if the probability is small, so it's 0.51 instead of 99.9, this value is also quite large. And this is basically telling per sample how sure your model is about the classification. If the model is absolutely sure, it means like this sample has been correctly memorized in the internal representation of the model. If not, it means that this sample has not been properly memorized. What you should do with a sample that has not been properly memorized? Keep it one more time. What you have to do if your sample has been properly memorized? Drop it, ¿vale? So here, basically, what you are getting is this idea of sequential. So I'm keeping everything, so I can see that the more sample I'm seeing, the raw value is decreasing, and this is without taking any kind of without taking any sample from the previous step. ¿Vale? So it's decreasing little by little, but not as fast as this one. ¿Vale? So with this idea, we say, okay, let's fix like a threshold to keep the samples. And this is basically what we did. No? We add here this threshold, we train our model, and we can see that playing with this lambda, we can get like a very good accuracy or low, but I mean, it's around 85 instead of, in that case, here, that it was more or less similar, but anyway, ¿vale? You can get basically the same values, even much better. The raw, depending on the lambda, you can fluctuate from 0 to 0.5, and this is the important part. So this is the number of samples that you need to keep on your computer when you are executing this sequential. You can see, even with the largest lambda, it means like keep the maximum number of samples. We're keeping less than 600 samples. That is much less like the one pass approach that we take 1,700 samples. See, is that clear, this point? So it seems it works, ¿vale? In the paper, if you're interested, we define some policies to define this lambda, and we can automate it, and we can make it dynamic depending on the phase of the training, etc., etc. But I think that for you, it's more than enough with all these ideas, ¿vale? Now it's time to see if this really works, because the two datasets I've been using as make moons and spirals is not really a business problem. So we decided to try this approach at scale. And what we did, do you know the UCI repository, data repository? So this is like the like the classical repository for machine learning datasets. There are around 100 datasets, ¿vale? Half of them classification, half of them regression, and it contains data that has been produced by research groups during, I don't know, 25 years. For example, no, one of the datasets that you have here is the iris dataset. You already know, no? The iris dataset. See or no? To classify a plant between iris setosa, versiculum. It's just a plant classification, or diabetes, or a wine quality. I don't know. There are many different datasets, ¿vale? So what we did is download all of them that are related with classification, in total 60, with enough number of samples. It means 100 samples at least, with at least 10 samples for each of the labels. And then we compute the z scores, standardize everything, divide it at random in train test, and then use this 60 dataset. We select at random 6 different classifiers: the AdaBoost, neural network, random forest, linear support vector machines, radial support vector machines, and XGBoost. And then we perform a simple grid search approach, and we deploy a model with these 60 datasets. So here you have datasets from different domains, different tasks, binary and multi-class classification, different original models, different grid search, etc., etc. Is that clear? Vale. Then what we did is now at random, let's copy these 60 classifiers, these 60 problems with a decision tree, a logistic regression, and a random forest. ¿Vale? And here, in principle, everything is in the diagonal, is that we get exactly the same thing. And if it's in this part, it's because the copy was better, and if it's here, it's because the copy was worse. So here we are comparing the original accuracy, the accuracy of the original model, with the accuracy of the copy. ¿Vale? Well, in decision tree, there are some of them that are not as good, but in general, you can see that all of them are on the diagonal. And here we are just comparing. So here we are comparing with the original, with the training data, and this is the comparison with the sampling, with the synthetic data. ¿Vale? ¿Sí? So more or less, brute force, it seems it works. ¿Vale? And now it's time to use it to. Well, and then this is for the this is for the single pass, and then if we want to try for the sequential, this is the comparison between the single pass and the sequential, and you can see that more or less are equivalent. ¿Vale? So even the data set is large, you can basically use the sequential approach, and more or less you get similar results. Well, here there is some of them that are not exactly the same, but well, that's not really important. Is that clear that it works? ¿Sí? Vale. This accounts for hours of computation, by the way. Vale. So now let's try to use it to real business problem. The first experiment, or the first use case that we use with this technique was what we call the obfuscation of risk scoring models. There is someone study economy here. ¿Algún economista en la sala? No? Well, so I can say bad thing about economy. So I can be bad with economy. There is an economist on the Zoom. No, they are sleeping, no problem. Bueno, so, ¿hay alguna pregunta? Son de aquí, bueno, no problem. Vale. So, I spent 3 years of my life creating risk scoring models. And believe me, it's a horrible task. You don't want to do that. How do they work? You have a data set, and then you have a Banco de España, or the European Central Bank, and then you need to make happy 3 different institutions, well, 3 different stakeholders. First of all, your boss, or your head. Second, the Banco de España, and third, the risk experts. And this makes deploying or developing a risk scoring model a little bit, let's say, I don't know, unhappy or uncomfortable thing. Because your boss wants that the performance of your risk scoring model is fantastic. The risk experts that are normally economists want that your model can be understandable by them. And the Banco de España or the European Central Bank limits which kind of machine learning model you can use. You can use decision tree and logistic regression, but not random forest. Why? I don't know. It's law. Vale? So the task, and at the end, what you want is create a linear model, a logistic regression or a decision tree. Tell me. It's accountable if you, depending how you define accountable. What's the difference between a random forest and a decision tree? Apart doing bootstrapping and... Sí. The 100 trees instead of one. What's the difference from a point of view of understanding what the decision tree, what the random forest is doing? It's the same that if you compare, if you are in a paper, you receive 1 review or 10 reviews. You can, at the end, you can understand from the 10 reviews if your paper is accepted or rejected, no? With a random forest, the same. See? It's just it's a matter of getting a longer explanation, nothing else. It depends, because you are assuming that you are that all of the 10 reviews should accept the paper. But if you compute the average, maybe you are lucky, and the the law of large numbers is going to tell you you have a 50% of probabilities of getting an accepted or rejected. Having more reviews is better than less. Vale? See, but well, the point is at the end, for me, a random forest is more complex to explain, but you can explain at the end a longer explanation. Vale? We will see one example later about that. Vale?
How the bank
¿Sí?
or say how the regulator is going to know what system have you used? I mean,
you need to
what system have you used? Everything.
And not everything, more than everything. You need to create an out of sampling. You need to provide the train data, the test data. You need to provide everything and try and press the button and check that and create a live report. Sí, sí. And a long report about 100 pages. Yes, exactly. And then you need to continue using the previous one. This is something that you need to do. It's like the verificant at the university. No? If you want to change the curriculum of the students, you need to explain everything and then they accept. If not, continue with the previous one. See? Vale. So you have like these 3 stakeholders and then you need to convince them that everything is correct. And at the end, what you are doing is trying to create a good model that is linear for something that is highly nonlinear. Because the world and the customers of a bank, they are every of them are different. Then at the end, what you do is you move all these nonlinearities from the model to the bid process. And then you start observing the data and say, if I combine the square of the income divided by the monthly expenses, multiply it by the zip code, assuming that you're living in the city center, pop, this is a highly predictive variable. This is what they did. And then they create that stuff. And then once they have this highly predicted attributes, they compute a logistic regression, they linearize everything with the transformations, and then say, this is my data set, this is my database, this is my model, it fits the regulation. Here you have the logistic regression model for risk scoring. But what's the problem? That now you have a beta that in principle should explain why your model is making a decision, but your variable is not explainable at all. Because what's the meaning of the square of your income divided by your monthly expenses multiplied by a binary value that says if you live in a big or a small city. This means nothing. So you are cheating yourself, ¿vale? So, but this works. This is how banks and many, this is how when you ask for a mortgage, this is what the type of things that the bank does with your data. See? Well, so what we can do with a copy, just generate samples here and use the complete pipeline and then create a copy that move from the input without the preprocessing to the outputs. So let's see if this works. So did you get the idea? Instead of having like your model, you will have your model plus the transformations. Vale. So we take a mortgage data set, and we create these 6 highly predictive variables. Vale? Well, the bank created, not us, but anyway. And then we train a logistic regression, and then we were able to get an accuracy equal to 77%. Vale? Easy? Easy business, eh? 1 minute. Vale. And then what we did is, let's take the original data and let's sample from the original data, create a decision tree, and use the labels that has been generated by these highly predictive variables, and let's see what's the result of what we get. No? So this is the average. Sorry, espérate, déjame que me pin. Vale, this is the tree copy accuracy. So it means like if we compare the accuracy of the logistic regression with this preprocessing with our copy, and we generate 100 trees. Remember that decision trees are super easy to do overfitting, and if you don't force like the seed, every time that you train, you will get a different decision tree. So what we did on purpose, we create 100 decision tree and see what happened. And this is the accuracy of the logistic regression, vale, for the synthetic data, and this is the accuracy of our 100 decision trees for the synthetic data. Here is the accuracy of our model with the training set, vale? Is 75, we lose 2% of accuracy, and this is basically the discrepancy. So we only get like at most, in the worst case, 15% of discrepancy. So it means like we can create a decision tree that is explainable without using these highly predictive variables that are not interpretable at all, and we can get similar results. See? And we can publish this, one of these models, as the model that is easier to understand for everyone. Vale? Well, another example. Imagine that again, you are creating a credit risk scoring, and then you need to explain and audit your model to different stakeholders, like the European Central Bank, and also your customers, no? But your customers is not the same to explain something to Jose than to my grandmom. My grandmom has a less knowledge than Jose. I hope so. My grandmom was super clever, eh? By the way, vale? See? So what does it mean? It means like for auditing purposes, we need to explain what we are doing to different stakeholders in different languages that are understandable for them. See? Because if not, an explanation has no sense if the receiver cannot understand what we are doing, what we are saying. So what we did is basically, I don't know if it was with the same data set or with another one, but anyway, we performed the same. I can't remember in the paper is written, but since I didn't copy this information to the slide, but anyway, we take a data set, we create a model, the performance was 0.79, and now it's time to explain to the different stakeholders how this model works. And then we have, for example, the European Central Bank that is super easy. So this is a random forest, if I remember. No, it's a gradient boosted tree. Oh my God, it's a super complex model to explain to an economist. What we did for the European Central Bank, we take the XGBoost, we copy it with a logistic regression because they are super familiar with logistic regression, and then we provide the betas, the most important betas. This is an explanation that is valid for the regulator because they know what we're talking about. See? But we didn't change the XGBoost. The XGBoost is already there. But we provide an explanation through copying of how the XGBoost is making decision. But my grandmom cannot understand what this means. But what my grandmom can understand is a decision tree. And even I can create different decision trees through copying, saying, hey, this is the simplest explanation I can do. A tree with one level, 2 levels, 3 levels. Of course, the larger the number of levels, the better so the lower the discrepancy. But anyway, I can, with a 30% of discrepancy, I can explain what the XGBoost is doing just with that. And then with 3 levels, it's here. The discrepancy is around 21. Only with this decision tree, I can explain to someone that is more intelligent or more can understand more complex things what the XGBoost is doing. So we are able to fulfill this idea of auditing and explaining to someone what it's doing. Vale? Vale. So what we are doing right now with that stuff, first of all, well, we have a project about copying machine learning models. And then one of the lines is using this idea of federated learning. Do you know what federated learning is? Well, so at the end, you have different data sets, different models, and you want to copy something that is collecting information from all of the models. So this can be thinking, you can think from a mathematical perspective of interpolating n different functions, or if you are more a machine learning expert, create an ensemble, a copy that is built on top of an ensemble learning method, or we can use even multi-label classification, assuming that for every instance, you have a different label. And then working with that, you can use copying instead of federated learning, that is a cryptographical tool that requires a lot of computation. Also, this is a research that I'm super interested in right now. It's the right to be forgotten. So every time that, imagine that you want to, this is a new European law saying that you can ask Google to forget everything about you. Do you know that? Did you know that? See? Vale. But what's the problem? Basically what Googling is doing is just removing data from the database. But it's not, Google is not retraining the model. So it means like if your data has been memorized by a model, your right to be forgotten is basically 0. Vale? And well, the idea of machine learning is you would like to create a model without retraining that looks like as similar as possible of a model that has been trained with the same database, just dropping or removing the samples that ask to be forgotten. Vale? Well, we are basically approaching this problem with copies in different ways, basically with 2 of them. The first one is change the way the empirical risk minimization formula, adding a new value to ensure that if there is something near to the sample that should be forgotten, if your model gives you the correct answer, penalize more than to force to forget this correct answer. And the other one is basically around this point that should be forgotten, just create samples and random them and label them at random. Vale? That's another way to allow, or to basically to create a hole in the decision boundary. And that's the last research line that we have in the project is we want to create a copy that is fair. Not only, so we want to replicate, to mimic the decision boundary, but forcing, for example, that there is no discrimination on male and female. And this can be basically done in several ways, but basically what we're assuming doing right now is that when we sample, we are able to fulfill the sufficiency criteria. That means like there is the same amount of errors and samples for both male and female. Vale? And that's all. I don't know if I spent too much time. A little bit, sorry.
A little more than usual, but okay, thanks a lot, Jordi. Questions? Not here.
No one understand anything. That's
And online, anybody writes? Or just mute off and say something? No?
Sure.
Yes.
The discrepancy level in your model was like 50%. I don't remember. On average, what is the, like, in real life, in a bank or in these situations, which kind of discrepancy you can expect?
From the copy to the original, you mean?
I mean, using this copy system, there will be one. Using another, like, just like
training,
will be another. Which kind of discrepancy I can expect from one model and the others?
It really depends on the task and the data. I mean, if there was like an universal good model, everyone will basically use it.
Nah, but I was asking just like a standard in the real life, maybe.
I don't know.
If I ask for a mortgage, I can expect that will be like a 25% of discrepancy.
Not really. No. So it really depends.
I just drop a coin. I mean.
So it really depends. So for example, I don't know what other companies are doing, but at least in banks, it's not the same. If you ask a small loan for, I don't know, do some refurbish at home, than if you ask for a large amount of money for a mortgage. In mortgage, usually there is a human who analyzes everything apart from, so you have your model, and then when the model gives the output, then there is a human verifies everything, because there is maybe right now I'm not so sure, but in principle 3 years ago there was no way to automatically verify that all the documents that you provide were correct. I mean, they ask you for your declaración de la renta for the last 5 years. Maybe now with a good AI system, you can take all the PDF and check that everything is correct. But traditionally, this screening was made by a human that understand every number of the declaration de la renta. I can't, but so in general, this is not a problem for a mortgage. Then for small loans, normally they are what they're called preconcebidos. So they give you already have, like, even you don't know. If you ask a small loan in a branch, the cashier in front of you has a number that tells you which is the amount of money that you can ask without going through the screening. Yeah, because this is the preconcebidos. It's like the kind of banners or things that you have in your mobile phone when you connect to your bank.
There was a question online because it was some noise before, no? So someone was going to say something. No? Okay. Okay. Well, so if there is nothing else, thanks again, Jordi, and well, he will be here just a few hours more. So essentially, if there is someone that wants to talk to him, just come to my office and talk to Jordi. Okay. So thanks again.
Welcome. Por la parte de las redes.